So in the previous lectures, we discussed the k-means algorithm, and also we discussed the mathematical steps involved in the k-means clustering algorithm, and also we discussed its pseudocode. So in this lecture, so k-means algorithm is one of the most prominent and also one of the simplest algorithms to implement for clustering of the data sets or clustering of images. And in this lecture, we are going to talk about some of the limitations, some of the prominent limitations of the k-means clustering algorithm. And then once we cover the limitations, then we are going to show the results of the k-means clustering algorithm on an image data as well as on simulated data as well. So the first limitation of the k-means clustering algorithm is that it works well only if the data set in the feature space can be separated into clusters that have a spherical or hyperspherical shape. That is the shape, when we are talking about shape, we are talking it in the feature space, which may be an n-dimensional real space. So when the shape of the data set in the feature space is spherical or hyperspherical, then in that case the k-means clustering algorithm is good for capturing the structure of the data set, and it constructs a nice spherical region around the centroids of each of the cluster. But if the data set in the feature space has some complicated geometric structure, then k-means algorithm may work very poorly for such kind of data sets. So here are two examples. So as we can see in both the images, we selected k equal to 4 for both the examples, and we can see that the data set has some complicated shape in this 2D space, and the k-means clustering algorithm doesn't capture the semantics of the dataset very well. So ideally the clusters here should have been, this should have been one cluster, this should have been the second cluster. So part of this data goes to this cluster and some part of this data goes to this cluster. Then there is this third cluster, and finally there should have been this fourth cluster. So this is what the ideal partitioning of the data set should have been, but the k-means clustering algorithm, because it works well only when the data set is spherical in shape or hyperspherical in shape in the feature space, it didn't work well for this kind of data set. Similarly, on the right side, we can see with k equal to 4, the partitioning of the data set is not ideal. So ideally this should have been one cluster, this should have been another cluster, this should have been one more cluster, and similarly this was one more cluster. So each of the trail in that data should have been a cluster, but the k-means clustering algorithm did a very poor job on this dataset as well. Even though the k value was selected appropriately, as there should have been a number of clusters in the datasets, but still the k-means algorithm was not able to capture the semantics of the underlying dataset. Similarly, we can construct two other examples. Let's suppose we have a data set that looks like this. So we have one cluster over here, and let's say we have another cluster over here. So we do not know like what is a boundary that the k-means clustering algorithm will give, but definitely it will not separate these two data sets, these two clusters, which should have been the ideal partitioning. So the ideal partitioning should be, this should be one cluster, this should be another cluster. But k-means clustering algorithm, if you run it on such kind of data set, it may give partitioning that may look something like this, or maybe something like this, or maybe like this. So even with k equal to 2, we may not get the ideal clusters even though they are very easily separable in this feature space, since there is not even the overlap between the different clusters. Similarly, if we take another example where, let's say, the clusters are circular, so we have this one cluster and the another cluster is inside this circle. So cluster number 1 and we have cluster number 2. So if we select k equal to 2 for this data set, we may get a partitioning like this or something like this, or maybe something like this. So since the data set is divided into the concentric circles, they cannot be separated by two different spherical clusters. They do not have this hyperspherical shape. So the k-means algorithm is not able to capture the semantics of the data well, and it gives very poor clustering results. On the other hand, if we have a data set like this, let's suppose we have cluster number 1, we have cluster number 2, and let's suppose we have cluster number 3, and even if there's some overlap between them, similarly we have cluster number 4. So in this kind of data set with appropriate value of k, let's suppose if we give k equal to 4, it may be the case that k-means clustering algorithm will give us the ideal centroids over here. So in a nutshell, one of the limitations of the k-means clustering algorithm is that it works well only if the data set has a spherical or hyperspherical shape or geometry in the feature space. The second limitation, the obvious limitation of the k-means clustering algorithm is that the value of k should be known. So for most of the real world application, it is very hard to assign the value of k. For example, let's suppose if you want to segment an image into, if you want to partition the images in a pixel into different regions, it may be very hard to determine how many number of regions are there. If we take this complicated image as an example, it may be very hard to determine how many number of clusters there should be. For example, this can be about one cluster, this can be second cluster, third, fourth, fifth, sixth, seventh, 8, 9, and so on. I mean, so basically, like, and now let's suppose if we want to have an adaptive algorithm that clusters each of the images as we obtain them from the cameras, then basically different different position of the vehicle may have different number of obstacles and different appearance of the environment. So it's very hard to specify the value of k beforehand. Even if we are not dealing with a computer vision application, let's suppose if we are just segmenting, if we are just partitioning or clustering a regular data set from a different field, it may be very hard to determine the value of k. So this value of k can only be determined experimentally. And there also we'll just never know the ideal value of k. So the number of clusters k need to be specified by the user, and selecting the value of k can be non-trivial task for many of the computer vision or other real world applications. So this is one of the very obvious and one of the biggest limitations of the k-means clustering algorithm. So there are ways to actually get around this, to solve this problem. For example, but there is no concrete way as to how to resolve this problem. So one of the methods that is typically adopted to or discussed in the literature to determine the value of k is known as the elbow method. And this is again an experimental method, so this is a heuristic. So in the elbow method, we run the k-means clustering algorithm with different values of k. And for each of the value of k, we plot the loss function. So let's suppose with this value of k, we have this loss, then we have another loss, and so on. And here it certainly starts decreasing. So the elbow method, and if we join this, So let's suppose this is k equal to 2, this is k equal to 3, k equal to 4, so on. This is k equal to 5, 6 and 7. Then we can see that there is a sudden change in the slope of this plot of loss function versus the k value. So this point, which resembles an elbow, which is a point where the slope suddenly changes, is actually denotes that increasing the value of k beyond this point will produce a very small reduction in the loss function, and before this point the reduction in the loss function is significant. So typically the elbow point or the point near the elbow point, for example the k equal to 5, can be selected as an optimal value of k. So at this elbow point the number of clusters are neither too large nor too low as well. So typically this is again a heuristic. I mean, there is no concrete way. It's again an experimental method. So we run the k-means clustering algorithm with different values of k, and then we plot the loss function with respect to k, and typically we select the elbow point or the point closest to the elbow point, or the point or one of the points in the vicinity of the elbow point as the optimal value of k. The third limitation of the k-means algorithm, so the third limitation, recall in the k-means clustering algorithm in the previous lectures we discussed that initially we initialize the mean values randomly, and this random initialization is one of the limitations of the k-means clustering algorithm. So this random initialization of the cluster means at the beginning of the k-means clustering algorithm can have huge impact on the quality of the clusters at the end of the clustering process. And a bad initialization can lead to very poor clustering results. And one solution is to run the k-means clustering algorithm with different initializations, and then select the initialization that produce the lowest loss function for any given value of k. So one of the solutions to this is that run the k-means algorithm, let's suppose some q number of times, where each time we initialize the means differently, and then after running the k-means algorithm q times with q different random initialization, so we'll have q different values of the loss functions. I'll p over the data set where p goes from 1 to q. So we select the final result as a one that produce the minimum value of the loss function. So this is one of the ways of getting rid of the effect of poor initialization. But as you can see, this is going to be problematic. For example, if we have 1 million, 10 million, 100 million data points, then running k-means clustering algorithm some multiple times is going to be computationally very expensive process and may turn out to be infeasible as well. So a better way is to use k-means ++ algorithm. So k-means ++ algorithm is an improvement over the naive k-means clustering algorithm, and there is only one difference. So the entire algorithm is same as the k-means clustering algorithm except the initialization. So it is the initialization of the means that differentiates the k-means clustering algorithm from the k-means ++ clustering algorithm. So if given a choice, you should always go with the k-means ++ algorithm rather than the k-means algorithm, since there is a better way of initialization of the means which may produce drastically better results. So this ends the discussion of the k-means algorithm. We have so far discussed the mathematical steps involved in the k-means clustering algorithm. We have also discussed the loss function. We have also seen how we can minimize the loss function in a two-step process, resulting in the k-means clustering algorithm. We also discussed the pseudocode as well as discussed the limitations of the k-means algorithm. So to summarize the limitations, the three limitations are: number one, the k-means clustering algorithm works well only if the data set D has spherical or hyper spherical shape in the feature space. The second limitation is that the value of k has to be specified which may be a non-trivial task for most of the real world applications, and this is one problem that is there in the k-means plus algorithm as well. So the k-means plus algorithm shares the same problem number 1 and 2 as the k-means algorithm, but the third problem in the k-means algorithm, which is the random initialization, this is one of the problems that is resolved to some degree in the k-means plus algorithm. So this summarizes the limitations of the k-means algorithm, and this ends the discussion of the k-means algorithm. So we will show the results of k-means algorithm on an image as well as on a sample dataset at the end of the k-means plus algorithm.